Hello, everyone. Welcome to the ILTA Physics Online lecture series. Today, we're going to study orbital motion, which is a type of circular motion. We've already learned that for an object to maintain circular motion, there must be a centripetal force pulling it toward the center of the circle. That centripetal force causes centripetal acceleration, which constantly changes the direction of the object's velocity. In orbital motion, the force acting as that centripetal force is gravity, which pulls the object downward. In other words, orbital motion is a special kind of circular motion where an object is continuously falling under gravity, but it never actually hits the ground. Let's first try to understand this type of circular motion from a macroscopic viewpoint as a kind of free-fall motion centered around Earth. Although the path of an orbital motion forms a circle, we'll start by looking at it qualitatively, using the ideas from two-dimensional projectile motion around Earth. Then, to analyze it more precisely, we'll derive several physical equations related to orbital motion using the relationships between free fall and circular motion. Finally, we'll think about the weightlessness that occurs during orbital motion. So, let's begin by reviewing some basic concepts that we need in order to understand orbital motion. First, to explain orbital motion, let's review projectile motion, which is one type of two-dimensional motion. Projectile motion is motion that's determined only by gravity. More precisely, it's made up of uniform motion in the horizontal direction and free fall motion in the vertical direction, forming a parabolic trajectory on a two-dimensional plane. When we analyzed projectile motion earlier as separate horizontal and vertical components, we made an important assumption. The Earth is large enough compared to the distance of the projectile's motion. In other words, we assume the ground is flat and that the direction of gravitational acceleration always points straight down. But what if the object's initial horizontal velocity is so large that we can't ignore it compared to the pull of gravity? What kind of motion would the object have then? The answer to that question is exactly what we call orbital motion, which we'll study today. And when we learned about apparent weight, we talked about weightlessness. We said that being weightless doesn't mean you have no weight. It means your apparent weight is zero. When a person or an object is in free fall, their apparent weight becomes zero, and that's what we call a state of weightlessness. In orbital motion, the same kind of weightless condition occurs. All right then, let's dive into this new topic, orbital motion, together. To explain an object's orbital motion, let's imagine this situation. As shown in the picture on the bottom right, an object is launched horizontally from the top of a very tall tower on Earth. When the object is launched from the tower, it moves as shown in the picture on the bottom left. It performs projectile motion, which combines uniform motion in the horizontal direction and free fall motion in the vertical direction, creating a parabolic trajectory. If we focus on the vertical motion, we can see that the flying object keeps falling downward due to Earth's gravity. Let's first think about the case where the object's launch speed is small. This corresponds to trajectory in the diagram. In this case, just like we learned before, the object follows a projectile motion similar to the one shown in the bottom left picture. Since the travel distance of a launched object is relatively small compared to the Earth's circumference, we can apply the flat Earth assumption. Then the object moves at constant speed horizontally, and it accelerates downward because of gravity, resulting in a parabolic path. Now let's imagine what happens as the initial launch speed increases. This corresponds to trajectory B and trajectory C in the picture on the bottom right. Since the launch speed is greater, the object travels farther and stays in the air longer. But take a closer look at the picture below. As the object is launched faster and travels farther while still falling downward, remember, Earth is round, so its curved surface affects the shape of the trajectory. If the initial speed is large enough, we reach the case shown as trajectory d on the right. In this case, even though the object keeps moving forward and falling downward at the same time, the curvature of Earth's surface matches the curvature of the object's path. When this happens, the object keeps falling and moving forward, but since Earth's surface curves away at the same rate, the object never hits the ground. It travels all the way around and comes back to its starting point, moving in a circular path. That's the principle behind orbital motion. Now, let's explain orbital motion a bit more in physical terms. Earlier, we thought about the conditions under which orbital motion can occur. We can understand this kind of motion by thinking about satellites that orbit Earth. The gravitational force that pulls the satellite toward Earth acts as the centripetal force that keeps the satellite moving in a circle. When that gravitational force is exactly strong enough to maintain the satellite's circular motion, the object follows a circular or elliptical path. That's what we call orbital motion. In other words, the object is still in free fall due to gravity, but that same gravitational force acts as the centripetal force that sustains the circular motion. So then, let's think about the direction of this gravitational force from a physical point of view. Before it's launched, the object sitting on the tower experiences a downward force due to gravity, its weight. Once it's launched, the object continues to experience the same downward gravitational force, as shown in the enlarged picture on the right. This weight, given by W equals mg, always has the same magnitude. Therefore, for an object in circular motion, as shown in the picture on the right, the gravitational force always acts toward Earth, which means the object is constantly being pulled toward the center of Earth. All right, now let's analyze this orbital motion quantitatively using physical equations. Orbital motion can be understood from 2 points of view at the same time. On a small scale, it's a free-fall motion where the object is constantly falling toward Earth's center. And on a larger scale, the entire path forms a circular trajectory, a circular motion. First, let's look at it from the free fall perspective. According to Newton's second law, the acceleration of a moving object is the net force acting on it divided by its mass. In orbital motion, the net force acting on the object is only its weight, and since weight equals mass times gravitational acceleration, the final acceleration in orbital motion is simply the gravitational acceleration, or 9.8 meters per second squared. Now, let's interpret the same motion from a macroscopic point of view as a circular motion. When an object moves in a circle, it needs centripetal acceleration. And according to the circular motion formula, that centripetal acceleration equals the square of the velocity divided by the radius. If we call the velocity of the orbiting object v-orbit, then by combining the definition of centripetal acceleration with the gravitational acceleration we just discussed, we can express the orbital velocity as the square root of gravitational acceleration time orbital radius. This equation is extremely important. It's the formula used to find the orbital velocity of an object in orbital motion. A good example of orbital motion is, of course, a satellite orbiting around Earth. Let's calculate the orbital speed of a satellite that's orbiting very close to Earth's surface, and also find out how long it takes to make one full revolution, in other words, its orbital period. Using the orbital velocity equation we just derived and substituting the proper values, we find that the satellite's velocity is 7,900 meters per second. Now, let's calculate the time it takes for the satellite to travel once around Earth, its period. In circular motion, the period equals the circumference of the circle divided by the velocity. So if we divide Earth's circumference by the satellite's orbital speed, we get a period of about 84.4 minutes. Finally, let's talk about weightlessness in orbital motion. Earlier, we said that orbital motion is both circular motion and free fall motion. And we also learned that an object in free fall experiences weightlessness. So, a spacecraft orbiting Earth, along with the astronauts and all the objects inside, are all in a state of free fall. And that's why they feel weightless, which means their apparent weight becomes zero. Therefore, it's important to understand that weightlessness doesn't mean there's no gravity or no weight. It's a condition that can only occur because gravity exists and the entire system is in free fall. Another well-known example of orbital motion is the Moon, which travels around Earth in an almost circular orbit. However, we cannot use the equation with the same parameters used earlier to calculate the Moon's motion. That's because the distance between Earth and the Moon is so large that the gravitational acceleration from Earth is no longer same constant at that distance. We'll study this part in more detail in the next section. That's it for today's lecture. Great job, everyone. See you in the next lecture.